job that we can in every single circumstance, because someone's life could depend on it. So do you need me to stop for a second? No? Okay. So yeah, we're expected to do the best job we can when no one's looking. So that's the integrity part. And I've started doing all my, I can't click forward, John. I started doing all my presentations starting out with that. So to get more to the subject that we're talking about today, ECG, principles of ECG. We're going to talk about cardiac structure, cardiac flow, electrophysiology, heart-related vital signs, ECG recording, PM pointers for PMs, and some troubleshooting. So let's get started with cardiac structure. The heart is made up of 4 chambers, 2 atrium and 2 ventricles. The atrium are the filling portion of the part, and the ventricles are the pumping portion of the part of the heart. This left and right side is divided by a piece called the septum. It divides the 2 sides of the heart. There's the atrial septum and the ventricular septum. When I used to work at Children's Hospital, we had a lot of kids that had surgery for, they call it an ASD, atrial septal defect, which is a hole between the 2 sides of the heart, which is a very common one. Now they do a lot of them in the cath lab. They used to do them open heart in the cardiac OR, and then ventricular septal defect, which is a little more rare, but it's between the ventricles. There's 4 one-way valves in the heart. There's the tricuspid, the mitral, and the pulmonary valve. And you can kind of look at these and kind of go, oh, well, the pulmonary has to do with the lungs. And hopefully aorta is the main artery that goes to the whole body. So hopefully you can kind of narrow that one down by a process of elimination. So that leaves you with the tricuspid and the mitral valve. There's nursing saying, people in nursing. Were you a nurse before? You are now. Okay, so good. You can correct me. You can correct me when I'm wrong. Oh wow. Oh wow. Okay. You have to get with me afterwards and let me know how I do. But if I say something wrong, correct me. So yeah, what we teach biomeds. Yeah. So the saying is try to be right. So the tricuspid valve is on the right-hand side of the heart, which is the lower pressure part of the heart. So that leaves you with the mitral valve, which is on the left side of the heart. So by process of elimination, knowing some of these terms, by looking at them, you can try to be right, and you'll have every valve figured out at that point. There's my saying for that. Valves, the saying is try to be right. This means that the tricuspid valve is on the right side of the heart. Pulmonary goes to the lungs, which you probably could figure out, and then the aortic is the main artery out of the heart. And it divides into ascending and descending. So sending blood above the heart or below the heart. Descending is below the heart, ascending is above the heart. That leaves the mitral valve, which is mitral valve is on the left atrium and between the left atrium and the left ventricle. I feel some pressure now that you're in the room. Hope I don't mess up. Oh wow, I skipped a bunch of slides there at once. Sorry. Yeah, I didn't mean to skip that many slides. I must have held the button down. Oh yeah, the mighty valve, the left side of the heart. Yeah, that makes sense. The people that are online, I have a cardiac nurse sitting in the room testing me. So she said that they also learned that the mitral valve, they called it the mighty valve because it's on the left side of the heart and it is higher pressure. So it's a higher working valve, more pressure on that side. So they call it the mighty valve. So the mighty valve, the try to be right, and then the pulmonary and aortic, got it figured out there. So being biomed techs, I like to have like block diagrams. So I found this on the internet, and I really like this better than like a lot of the other pictures that I've seen of cardiac flow. So if we look at this up here on the board, or on those of you online, the right atrium, so everything from the body comes from this AP vena cava over on the top right. That's ascending and descending vena cava, goes into the right atrium, and that's a filling chamber. And from there, it pumps through that tricuspid valve, try to be right valve, into the right ventricle. And we said the ventricle is a pumping part of the heart. So this pumping valve pumps through it's a semilunar valve called the pulmonary valve, out through the pulmonary artery, which the blue parts are deoxygenated blood, and then the red parts are oxygenated blood. So once the blood gets oxygen, it's red, and before it's blue, just part of this diagram, the way it's drawn. And I've seen a lot of diagrams that are drawn this way, red and blue. So arteries carry blood away from the heart. I always remember A for away on the artery. And the only arteries in the body that carry deoxygenated blood are the pulmonary arteries. And then from the pulmonary artery goes to the lungs, gets oxygenated, so gathers oxygen in the blood, exchanges gases there in the lungs. The carbon dioxide goes out through the lungs and the blood picks up oxygen. Pumped back through the pulmonary vein, which veins carry blood back to the heart. And in this case, this is oxygenated blood. Normally veins carry deoxygenated blood. So the only veins in the body that carry oxygenated blood are the pulmonary veins. So it's kind of a trivia question, I guess. That's why I kind of put that in there. From the lungs, it goes to the left side of the heart. Left side of the heart is a bigger, more muscular part of the heart, and it's more for pumping to the body. And we'll see, I have another slide in just a second. We'll talk about systemic circulation and pulmonary circulation. But from the left side of the heart, it fills again into the left atrium, pumps through the tricuspid valve, which we said was the mighty valve, the mitral valve, over to the left ventricle. Left ventricle is a pumping part of the heart. And in this case, it's pumping to the body. This is called systemic circulation. And that's that aortic valve, the semilunar valve on the bottom there. Out through the aorta to the ascending, descending aorta, out to the body. Repeat all over again until you die. Or have open heart surgery and they put you on bypass. Cardiac flow, so this is pretty much saying what I said in the last page. This is pulmonary circulation. This is the right side of the heart, inferior and superior vena cava, IVC and SVC. So inferior is the lower part of the body, superior is the upper part of the body, emptying back into the right atrium through that tricuspid valve, over to the right ventricle, out through the pulmonary valve, to the pulmonary aorta, or pulmonary artery, sorry. Whoa, this thing. Sorry about that. I need to click it very quickly. Did you have this problem, Brian? So deoxygenated blood goes to the lungs, and then it's oxygenated. From the lungs, it goes back through the pulmonary veins, back to the heart, to the left side of the heart. Left side of the heart, pulmonary veins fill into the left atrium, pumps through the mitral valve to the left ventricle, which the ventricles we said are pumping part of the heart. So this part is pumping out to the body. This is called systemic circulation. The other part was called pulmonary circulation. I thought, there we go, there's my cool block diagram on that. So if we look at this one, we can see at the top On the left-hand side, we have the pulmonary artery, and we see that that's to the lungs and it's pulmonary circulation, then the pulmonary vein. So that's the part that makes up that pulmonary circulation. And then at the bottom, sorry, we have the left ventricle, LV, and it pumps out through the aorta to the body, and then back through the vena cava, the superior and inferior vena cava, back into the right side of the heart. That part to the body is called systemic circulation. So we have two types of circulation in the heart, pulmonary and systemic. I gotta click this really, really fast so I don't skip a bunch of slides. Electrophysiology. So the electrophysiology is the part that makes the heart work. It's the electrical part, electrical impulses that cause those muscles to contract in the heart and pump the blood. So this is called automaticity. It's a mechanism for normal heart rhythm. And you can see on the right-hand side, we have electrical conduction system. We have SA node, AV node. We have on the right-hand side, atria and ventricles. And we can kind of see a pathway there, a conduction pathway, which we'll talk more about on the next few slides. Oh, man, I got the bummer one here, man. When I go back, it seems to go okay. ECG is the same thing as EKG. So ECG or EKG, what do you say? What do you say in the hospital? EKG, oh, okay, that's like a 12-lead chart or whatever that you're talking about. Okay, so she said it in the cath lab and that they talk about ECG, but when they want to, the paper reports and it's an EKG. So they're the same thing. The word, when the word electrocardiogram is translated into German, it's spelled electrocardiography with a K. And so that's where that comes from, the root of that word. EKG is just what some people say instead of ECG is based on this translation. So Brian and I were talking about this. Brian's in the back of the room there. And we said like the cart is usually like what referred to as an EKG. And then ECG is like just a lead, like 3 lead or whatever, not as many leads. I also have heard before ECG that they say EKG because sometimes it gets confused with EEG, electroencephalograph, which is looking at the brain. So for electrophysiology, we have a natural pacemaker of the heart. It's called the SA node, and it's located on the right atrium. It initiates an electrical pathway responsible for normal cardiac conduction, proper filling and ejection of blood from the 4 chambers. It causes the atria to contract and fill the ventricles. So everything starts at the SA node. From the SA node, it goes to the AV node, the atrioventricular node. So if you like kind of break down that word, you'll know that it's at the junction of the atria and the ventricles. It receives conduction impulse from the SA node. I had earlier this year, I was in the EP lab. Brian, the guy that I was talking about that's in the room, one of my friends, he works on cath labs, and it was actually one of his cath labs that I was at visiting. I had atrial flutter, which is a misconduction between the SA node and the AV node. It was going crazy, but it wasn't happening all the time. It was just some of the time. So when I got diagnosed with it, I think my ventricular heart rate was 140. My atrial heart rate was like 300. So I had 2 beats on the atria for every 1 beat on the ventricles, and my heart was going crazy. And I was just sitting in the waiting room at the doctor's office, just went in for a normal screening. But they started telling me, you have a part that's misconducting, and I said, is it between the atrial, the SA node and the AV node? And they said, yeah, like, where do you work at? What do you do at the hospital? And I told them, I work in biomed, but I also teach a class on cardiology too, to biomed techs. So I kind of know this a little bit, but I don't know much about arrhythmias. one of the cool things I found out about that arrhythmia, the atrial flutter, I said, how do you know, because looking at it, it looked pretty normal, the ECG, because you're used to seeing your ECG printout on your SIM. When you put your patient SIM on there, you're used to seeing that. And I thought, well, it looks pretty normal, but it's just very fast, is what I thought. The doctor said, if you flip it upside down, it looks like a sawtooth, is how you can tell atrial flutter, which I learned something by experience, by having a problem myself. So I got a cardiac ablation procedure done to burn those pathways that were going crazy, and pretty much don't have atrial flutter anymore. Now I have AFib very infrequently, but I take now blood thinners and medication to keep my heart from going too high. Metoprolol, it's called. I think that's how you say it. Yeah. So it's a beta blocker that keeps my heart, because they were found out when I was on a Holter monitor that when my heart rate got high is when I went into AFib. So they keep my heart rate down until I get in the room with someone correcting me on my presentation, and my heart rate goes up a little bit. So AV node, atrial ventricular node, receives the impulse from the SA node. The AV node relays the impulse down the ventricles through the bundle of His. The bundle of His is more in the ventricular area of the heart. Bundle of His branches into right and left for the right and left ventricles. These bundle branches break into Purkinje fibers. This leads to ventricular contraction and ejection of blood. So we're going to look at this same diagram again, and now we can see where the SA node, the AV node, and then if you look down at the bottom, the middle part there is the bundle of His, and then the Purkinje fibers are kind of towards the end, the outside part of the ventricles. At the bottom, that V-shaped kind of, or W-shaped at the bottom. And that's what we're looking at on an EKG or an ECG. We're looking at the heart in 360 degrees here of this. So the first part is the P wave up at the top, atrial depolarization. Depolarization is the contraction. So then the atrial contraction, then we go to the Q wave. I'm kind of just going around the circle. The Q wave is the start of the ventricles depolarization. Then the R wave, which is the big part, which is the big up sloping part of that wave, which I always kind of remember, like the big part goes with the bigger part of the heart, like the more muscular part of the heart, which is the ventricles that pump. So both ventricles pump at the same time, left and right. Same with the atrium, left and right pump at the same time. To that part is called the QRS complex. The big wave, the small wave at the beginning, the tall wave, which is the R wave, and then the QRS at the bottom. Ventricles contract during that part, so the bigger part of the wave goes along with the bigger part of the heart contracting. Then it goes through repolarization, which is the T wave. Repolarization, I always try to think repolarize, relax. That's the relaxing part of the heart. When it's relaxing, and then it's filling again. The atria are filling again. And then the ventricles fill after that. So then the end is the T wave, which is so that's what we're looking at with our SA node, AV node bundle of His Purkinje fibers. That's what this represents. Being a biomed, I like colors and block diagrams, and this to me like kind of broke it down very good because I could see where everything kind of happens, where everything starts at. So the P wave, the Q wave, which is that very small orange segment, then the R wave, which is that bigger red wave there. The S wave is the purple part, and then the T wave is the blue part at the end. And there's a lot of different measurements you can do off of these waves, different between the intervals of each one of them. You see the P to R interval, P to R segment, Q to T interval. And I know like some of our monitors in our ICU, we do QT measurements on patients in the ICU. I don't know what it really goes along with. I think it's how long it takes the heart to refill or relax. Is that? Oh, okay. So she said that some medications prolong the QT interval. So they might have to adjust the dose of medications if the QT is too long. That's a number that just pops up on the screen in some of our ICUs. One of the ICUs I work in is the cardiothoracic ICU at work. So I see it on the monitor, but don't really know a lot about it. It either works or doesn't work. It's one of those things that, why aren't we getting our QT measurement? Probably your leads is the most common thing. So, oh man, just when I thought I had it figured out, this clicker. So electrophysiology, not to beat it to death, but this is a good representation, P wave depolarization of the atria in response to the SA node triggering. The P to R interval is the delay of AV node to allow the ventricles to fill. The QRS complex is the depolarization of ventricles triggering the main pumping contractions. S to T segment is the beginning of ventricular repolarization, should be flat. And then, although in that drawing it doesn't look that flat to me. Then the T wave is the ventricular repolarization or relaxing. So that's what's happening during our ECG. So how do we, on a normal ECG, we have 3 leads. There's a good way to remember these, and it's by the number, how many L's there are in each one of the leads. This is, Jose, do you remember this from CBT? I think it's the same exact slide. I mean, I'm the owner of this slide. I made this up myself, so I'm keeping it, even though a lot of that stuff was sold to Amy. So 3 leads. Lead 1 is measures the polar difference between the right arm to the left arm. So right arm to left arm. Lead 2, and there's 1 L in there, so you see the L underlined. Lead 2 measures the polar difference between electrode on the right arm and electrode on the left leg. So you see there I underlined 2 L's for the left leg. So it goes across the chest. And then lead 3 measures the polar difference between electrode on left arm and electrode on left leg. So LA to LL, and I underline there's 3 L's there. This is called Einthoven's triangle. Another thing to note is that lead 2, since it does go across the chest, it measures respiration rate based on impedance changes in the chest. As the chest rises and falls, the impedance changes. So we get different impedance equals respiratory rate. Okay. I need to click it really fast. Sorry about that. So another nurse saying, it's funny having a nurse in the room talking about nurses. So white is on the right arm, black is on the left arm, and red is on the left leg. And there's a saying for that. It goes white on right, smoke over fire. Do you remember this one too, Jose? From the CBT review. Meaning that the white is on the right arm, the smoke, which is black, is on the left arm, and the fire, which is red, is on the left leg. So the smoke is over the fire. So an easy way to remember the colors of ECG leads. White on right, smoke over fire. And I've seen that even in nursing units. I hate to badmouth nurses with the nurse in the room, but I've seen them reversed before, especially the black and the red. Seems like that's an easy one to reverse. Heart-related vital signs. So based off of the heart pumping and sending blood, we get a lot of other heart-related vital signs. One is invasive or non-invasive blood pressure. We have the systolic blood pressure, which is the heart pumping, ventricular contraction or depolarization. It's the ejection of blood into the body, creates a pressure. And then when the heart is relaxing, we get our diastolic pressure, the bottom number on our blood pressure reading. So it's systolic over diastolic. And I always remember diastolic as the denominator. Someone told me diastolic for down, like the down number, D for down. So that's your invasive, non-invasive pressure. The invasive pressure is just a static, more of a static pressure with the heart pumping, because there's always pressure on the arteries. And normally normally it's art lines, not too many CVP lines, central venous pressure, CVP. Pulse oximeter. Pulse oximeter is based on pulse and flow of blood and circulation of hemoglobin, which is red blood cells. Red blood cells are what oxygen binds to in the body. So depending on how much oxygen is bound to your red blood cells, you get an oxygen SpO2 reading on your pulse oximeter. And then another cardiac related vital sign is cardiac output. It's the output of the heart, how much blood it's pumping in each stroke, or liters per minute stroke. Stroke volume, how much is pumped, times the heart rate, how fast the heart is pumping, equals cardiac output. Do you guys use continuous cardiac output where you're at? Yeah. Mm. Oh, so you'd use thermal dilution method then? Yeah, yeah. That's the most common thermal dilution method. I'm not going to get into that in this presentation with the Swan-Ganz catheter, but there's also another technology called continuous cardiac output, which I used to work at a children's hospital. I never heard of it before. So when I started working in an adult hospital and I do that cardiothoracic surgery ICU, which is all the patients that have had open heart surgery recovering, we have continuous cardiac output. And I thought, man, this is really cool. How does it work? You know, like, what are they doing? And I'm not going to get into all that in this presentation, but it's kind of beyond the scope of this, but kind of a neat way to do cardiac output. And that's, and a lot of time in ICUs, cardiac ICUs, is cardiac output is a big deal. Man. Presentation is going to be 5 minutes longer, just going back and forth on all the slides. So 12 lead ECG. If we look up at the top, we have lead 1. I'm going to go over to the right. We have AVR, V1, V4, and then the next line down, we start with lead 2, which is the most common lead we see on patient monitors, right? It has the highest going R wave. So lead 2, then we go to AVL, V2, V5, and this is the typical configuration. The configuration can be changed, I think, the way it prints, but most people are used to looking at it this way. Most cardiologists want it this way. Lead 3 at the bottom, and then we go into AVF, V3, V6. That's more looking at the left side of the heart. Yeah, sorry. Oh, the AVL is also left side of the heart too, I guess. Augmented. Okay. Wow. I need to get with you after the class. So lead 2 at the bottom is just all lead 2. It's no other leads on there. See if I can get this to click. Only one slide. So 12 leads, ECG, our leads are right arm, which we know is white, our left arm, which we know is black from the white on right smoke over fire thing, and then our fire part is red, that's the left leg, and then our RL, or right leg, is green, and I always refer to it as reference lead, as RL, and it's green. And I kind of remember that also green for ground, because ground is on our power cords is green. So we have white, black, and green on almost power cords. So I remember green is always the ground. The same on ECGs. It's kind of the ground, it's the reference lead. V1 is brown, all the rest of the leads are brown. And they're just labeled V1, V2 through V6. So if we count these, there's only 10 leads. So we have what right arm is 1, left arm 2, left leg 3, 4 is right leg, and then we have 6, 1 through 6. So how do we get 12 leads? We have what's called augmented leads. The augmented leads are the AVR, AVL, and AVF. So the augmented AVR is augmented voltage at the right arm, AVL is augmented voltage at the left arm, and then AVF is augmented voltage at the foot. These leads do not have an electrode connection, so they're calculated based off of those other leads. There's actually no AVL, AVR, AVF. If you're looking at the lead wires on your ECG box, you're never going to find those. It's all calculated. So we only have 10 leads, but that makes a 12 lead ECG. And we're only looking really at nine of those leads because we have one of them is our reference lead, our RL. So we're looking at 9 leads plus the augmented leads equals 12. Man, I don't know why I can't get this. Huh? And some of them are very, very small. I think it's the AVR or AVL that's really, really small. So the degrees of ECG, all these different leads are looking at the heart from different angles. And this diagram kind of, that's what it's talking about here. And you can see how some of these are different sizes based or inverted or whatever based on where it is looking at the waveform. Graph paper. I always go over graph paper with biomed people because it always seems like it's a surprise to some people what all those little squares are on the graph paper, and we should be looking at that every single time we do a PM on our paper. And I think it's something that sometimes shows up on the CBT, the Certified Biomedical Equipment Technician test, and it's also something that we've always had in our CBT review too. So this is important to know the graph paper for biomed techs, in my opinion. So the time of graph paper, your normal paper speed is 25 millimeters per second. Alternate speeds are 25 is our normal speed, 50 and 100 millimeters per second. So the amplitude is typically 10 millimeters or millivolts. So that's the upward part. The time part is the part going, oh, you got me another clicker. Oh, you got tired of me flipping back and forth? Turn this one off. Make sure this one works. It's turned on. Oh, better. I like that. Okay. My clicker in the room, those people online, my clicker's got, for advancing the slides, has been replaced. So hopefully I don't keep on going crazy on these slides, going back and forth. So the time is going across. It's kind of like, I think of it like an oscilloscope. The oscilloscope, the vertical trace, or the horizontal trace is time, and the vertical trace is amplitude. So I think of it kind of the same way. And the alternate speeds on the ECG graph paper, that going to 50 or 100 millimeters per second, that stretches out the waveform. So the doctors are able to look at it more precisely in certain areas and be able to measure things a little bit better than it is kind of scrunched up at 25 millimeters per second. Do you really see that very often in practical use? Oh, what's in the EP lab? Yeah. So they can look at it more in like closer, what's happening during each part. Yeah, kind of. So she said that in the EP lab, they look at with different systems, they sometimes extend the speed out a little bit more so they can look at it a little bit better, kind of like what I said. ECG timing. This is an interesting slide. Beats per minute. This is lead 2, which we're looking at here. But if you can see, depending on where you start at, how many squares go by. So if we start at that first R wave on the left-hand side, and if we had an R wave at the first marker, that only 5 millimeters after. So this graph, I'll go back, take a step back. Dave, you're going too fast. The graph paper, if you look at it, you see bold squares and you see small squares. The little squares are 1 millimeter each. The bigger squares are 5 millimeters each. So if we had a heart rate starting at that one on the left-hand side, that R wave on the left-hand side, it's right on that bold wave there, on the bold graph paper. If we go to the next bold paper, that if we have another heartbeat there, it would be 300 beats per minute. And as we count out, same thing. But the big one that I want to talk about is where we have 60 beats per minute. That's at 60 beats per minute, we have 1 ECG per every 1 second. Interesting, because pretty much every ECG simulator that I've ever seen has a 60 beats per minute setting on it. Wonder why that is. We'll look at that a little bit more. So ECGs normally are printed on a grid. The horizontal axis represents time, and the vertical axis represents voltage, like we talked about on that previous slide. A small box is 1 millimeter by 1 millimeter square. It represents 0.1 millivolts. So 10 of those equals 1 millivolt, or 0.0001, and 0.04 seconds, or 40 milliseconds. A large box is 5 by 5, 5 millimeters by 5 millimeters. I'll go back. These are the boxes I was talking about on this slide, the bold boxes and the not the really small boxes. So the bold boxes are the large box, which is 5 by 5. Represents 0.5 millivolts, so half a millivolt, and represents 0.2 seconds. So 5 of those would equal 1 second, right? So that's where we get our 60 beats per minute, and we have 1 second, 1 heartbeat every second. The large box is represented by the heavier line than the small boxes. I have a rate equation on here, which I like to do this every now and then when I go up to patient rooms and just messing around, you know, like get my little calculator out on my phone and calculate heart rates, and then look at the monitor and see what it's saying. If I see a printout, just like, I guess because I'm a nerd. Most biomed people are kind of nerds too. So, but in a group of nerds, I may be like more nerdy than even the nerds are in there. So the rate equation is 0.04 times the number of squares. So if you look up top, we see the 1 millimeter by 1 millimeter equals 0.04. So we can easily calculate, you know, like the bigger squares are 5, so we could take 5 times 4 equals 20 plus 1, 2, 3, 4, whatever, and calculate that times 0.04. Then answer times 60 equals our rate. So graph paper, this is what we were just talking about, the big squares and the small squares. So 1 millivolt, if we go back and look at that EKG printout, the page with the 12 lead, all of them start with this big square wave at the beginning. That's a reference for the doctors looking at this ECG, and they know that that's 1 millivolt. And it takes up 10 little squares or 2 big squares, 2 of the bold squares, or 10 of the little squares. So 1 millivolt is 10 millimeters high, and it's a reference pulse. One large 5 by 5 is, or one large box is 5 by 5 represents 0.2 seconds or 200 milliseconds, and time in 0.5 millivolts amplitude. And then the small squares, same thing. And we can see that horizontal axis, that we're going to the right, it says time, and then our vertical axis, which is our amplitude, our voltage. ECG simulator, I know like when I refer to a oscilloscope as being that, that a lot of people don't really use oscilloscope anymore. Like most new techs, I don't even know if they teach oscilloscopes in school anymore. It was one of the things that we learned a lot on when I was in biomed school a long, long time ago. But when I say, oh, it's just like an oscilloscope, I kind of get the confused look on some people's face. Like, oh, okay, I need to explain that a little bit more. And on our oscilloscopes, we can change how much voltage and how much time is per division. So it's a little different than the ECG where we're kind of stuck with the same amplitude all the time, but we can change the time period on an ECG based on the printout time. Test equipment, ECG simulator, set to 60 beats per minute. Why 60 beats per minute? So we have one R wave every second on our 60 beats per minute. Every simulator, pretty much like I said earlier, has this 60 beats per minute setting on it. So the normal paper speed is 25 millimeters per second. We set our ECG sim to 60 beats per minute, so we have one heartbeat every second. Count the number of squares on the paper. Should be 5 big squares or 25 small squares. Then you know your paper speed is the correct speed. It's kind of a calibration thing. And doctors are never going to know that, or nursing staff is never going to know that, because they don't have a standard like we have with our ECG simulator. That's a test standard, that ECG simulator. So it's a calibrated piece of test equipment that we're using to set it 1 per second, and we're able to tell if that paper speed is correct or not. And I've seen like the little strip recorders on patient monitors. Sometimes they're not quite exactly right, but if you're testing an EKG, the cart, it better be right on the money, because that's the one where they're doing diagnostics off of. The ECG strip recorder, the little strip recorder, is just kind of a tool to see if more is needed. Like they order an EKG, right? Like the cart that comes into the room, and someone from cardiology will set up the patient, right arm, left leg, right leg, V1 through 6, and do that 12 lead ECG. But that one has to be, when you're checking those, needs to be right on the money, that 5 millimeters, or sorry, 5 squares between each heartbeat at 60 beats per minute. And I have a paper here. This is a ECG that I ran, or EKG that I ran at work. This is off of, I believe it was a Philips system. I kind of blacked out some of the areas where I was at, but BTU is where I was working at, and the date down there, 6/29/20. If I look at this though, I start looking at it closely, more of this on this ECG. At the bottom left, I can see some stuff here. I see speed, 25 millimeters per second, limb, 10 millimeters per millivolt, and then chart, I think that's chart 10 millimeters per millivolt. Then if I look over on the very far right-hand side of this graph paper, I see that calibration pulse. So I look down here and I see that it's limb 10 millimeters per millivolt, and I go, oh, there's 1 millivolt right there from that baseline up to there. Is the baseline's not quite on the bold line, so it's 1 below the bold line, and then the top part is one below the bold line there. So I know it's 10 millimeters. I have the ECG sim set at 60 beats per minute. So I can go up to this top, we'll go to lead 2 here on this ECG. And it starts one after the bold line. Then I go over to the right, and I can see my next ECG R wave is 1 after the bold line on the right. So I know my paper speed is correct. And that's one of the key things I'm looking at on this ECG printout using my test equipment. And then of course, I'm gonna measure that 1 millivolt square wave at the right-hand side. I'm gonna count those squares and make sure. That's something that probably the doctor looks at too. And I mean, if that was off, we would definitely hear about it in biomed. That would take like 1 second and they would know that. They probably know that better than we do. But the standard of the speed part, they don't have a standard to check that. That's what we're doing with our test equipment. Troubleshooting. Noise on ECG or not picking up a lead. See if you can connect your lead, the lead set to your simulator. That's like the #1 thing we want to do as a biomed. So we have a good standard. We have our standard, our calibrated test equipment that we're going to hook it to. So we have a known good source of ECG. Check all the leads on the monitor or cart, electrical and mechanical connection. I know on the 12 lead, or 10, it's actually 10 lead, but 10 leads, we have the trunk cable, which is like from the ECG box, we have a cable that goes out to the patient. And then on the ones that I have, we have a short little lead that's like maybe 6 inches long. Do you guys have that? And ours have alligator clips on them. What I do is the stretch test on those. I kind of pull on them a little bit. If they feel like a rubber band, usually they have a bad connection. And you can take your meter and go across it and test continuity and see if you have a bad connection there. But first I start with the stretch test. If it stretches at all, throw it in the trash. Check all leads on the monitor or cart, electrical connections. That's kind of what I was talking about there. And sometimes you can see, physical damage, but not always. If it reads good on the simulator, there's something wrong with the patient, with probably electrodes or electrode placement, or how long the electrodes have been on the patient. They dry out over time. Patient, have nursing check electrodes and replace. They can get dried out. It's funny because whenever I go on a troubleshooting call for ECG, you always say, like, when's the last time you replaced the electrodes? And the answer is always, oh, we just replaced them not that long ago. Like every single time, like we just replaced them not that long ago. I don't know how long not that long ago is, but just for me, can you change those while I'm here so I can see, and look at the package that they're in also, because that package, once they tear that package open, it starts drying out too. So sometimes they dry out in the package. So you might have just replaced them, but you replaced them with some more bad leads that are dried out. So that's a little trick there, and that's also another thing to check on ECG carts. I know everybody, or not, ECG carts, when you do a PM, you look at the dates on all the leads that are in the envelopes that are hopefully stored with the ECG cart. If they have ones that are past their expiration date, throw them away. So make sure the skin is prepped, which is not really our job, but you can watch if the nurse replaces the electrodes. Alcohol wipe to get the oils off the skin, scrub a little bit. Should be a little red. That's just from like textbooks that I read. And also hair, people that have a lot of hair. I know when I had my procedure earlier this year, they shaved my entire upper body pretty much. I was like, wow, this is gonna suck when it grows back. It's very itchy. So I had no hair left on any, I didn't have to worry about having hair in the way because I had none. Elderly people get really very dry skin. So sometimes dry skin can cause artifact also. So having your ECG simulator and being able to test your ECG leads on the patient, you can eliminate patient or monitoring system pretty quickly with that ECG sim. Troubleshooting. This is more of like I guess, CBT question. Does not read lead 1 or lead 2, but reads lead 3. Process of elimination tells us that left arm is good, left leg is good. That leaves us with the right arm that's bad in that part. So check the right arm leads and cabling, then patient electrode and placement. So sometimes if it's placed on a bony structure, like more on the shoulder, it can read bad. I know it's called left arm, but it's kind of more left upper chest than it is left arm. But it should be on more of a meaty area of the body, not on the bone as much. That can cause bad ECG readings. And you can see this is the Einthoven's triangle again we were talking about earlier. Questions